Brazil. Thank you for this kindly invitation and also this kindly introduction. So I'm so happy and the pleasure to be here with you for this talk. I believe everyone here can hear me, okay? And my screen is being shared well, okay? So let's start because now I can't see any message from the chat. So my talk here is about computational tools, okay, techniques in designing materials. If you, for example, point out your camera to this QR code, you can open, okay, our research website, and there you can see more information about our research group. Here is my email, and then you are interested to talk more or write to me, please, you can write. So let's start from my city. Okay, welcome to Niterói City. I can show you here the map. Niterói is exactly this border in red that you can see, okay, quite close to Rio de Janeiro, the famous city in Rio de Janeiro, in Brazil. Here's Rio de Janeiro and many city tours. So here we have the ocean and the big bay in this entrance, as you can see. Our campus is located here, close to downtown in Niterói. As you can see on the right side, this is our campus, and here is a view of Rio de Janeiro city from Niterói. So we here in Brazil, we would say that the best view of Rio de Janeiro city is exactly the view from Niterói. Okay, so more about Niterói. Niterói is a quite wonderful city with many beaches, and sunset is wonderful every day over the year. Here is the campus, well located, close to the Guanabara Bay, with these views here. So it's amazing, and I'll be happy if you can join us and visit us. Here in our institution, we have a master and PhD program in chemistry. Well, and high score here in Brazil with very good concept, okay, and score. The coordinator of our program today is Professor Julio Martins da Silva, being auxiliated by Professor Tiago de Melo Lima. Like if you have interest, we have two men, okay, entrance in our PhD program. Actually, exactly now, this week, we are having registration for the PhD program. We have a registration at the beginning of the year. In general, at end of January and beginning of February, we have registration. And also mid-year, like June, July, you have another entrance, okay, to the program. So if you can see more, if you want, you can see more news and information, click on this QR code, okay, on the screen. So who I am? I'd like to introduce me, okay? I actually I think my friend was like quite wonderful talking about my career, but I'd like to highlight some aspects, okay, about this pathway, okay, to you. I did my PhD at University of São Paulo. University of São Paulo in Brazil, again, they is the most important and greatest university in Latin America, and University of São Paulo is within 150, okay, top list of universities in the world. So I developed my PhD in molecular laboratory and spectroscopy, advised and supervised by Professor Mauro Ribeiro. And after this period, I performed a short period, 2 years, as postdoc there at the same lab, developing some continuum atomicity hybrid codes be applied for fluid studies. And in 2009, I started a collaboration with Professor Dave Vanderspoel. Okay, in that moment, the man developed of Droma package. I will show you about this package soon here in my presentation. And also in 2010, I started another important topic in my formation uh, here where I stayed in Jülich, okay, a lab, okay. I can show you later on about this as well. So I started my career in a federal university in Minas Gerais between 2009 and 2013. In 2012, I stayed for a while as visiting researcher and working with Professor Edward Magin, University of Notre Dame. And also between this period here in 2015, I stayed as postdoc researcher working in the materials physics group Uppsala. It's a huge group leader by Professor Eriksson, and Professor Carlos Moisés was the professor in that moment that I was working on. So in 2013, I started my position in Fluminense Federal University until now. I also working with Professor Daniel Brandel, one of leaders in batteries at Uppsala University. So as my colleague said before, in 2020, together with 3 other colleagues, I started a new startup in silico design. In silico design is a startup where the main focus is to use computational chemistry techniques and artificial intelligence for designing molecules and materials. So if you want to know more about in silico, you can click on this QR code in your screen, okay? And then in 2020, 21st and 23rd, I started a new collaboration with other researchers from Uppsala, Professor Amber Mays and Heather Yunus. They visited Brazil recently to join us here to work with us. And also, we have a very good collaboration and productive collaboration with Professor Ulf Björnholm. Professor Ulf Björnholm is a leader in XPS, spectroscopy in Uppsala. So, with that, I would like to show you also that moment, 2010, that was quite important to me. I believe, for example, here in this general pub watching this presentation, we have many young students, women students, men students here watching. I'd like to inspire you saying that this type of school is quite important for your community. So that was quite important for me. I attended this winter school in 2009 with big guys here, like 2 weeks, having classes, intensive classes by theoretical methods and also practical classes in Jülich Supercomputer Center. Here is me here, okay, signing by this group. This was like quite important for my formation because like cover exactly the many techniques, computational techniques that you can see here in this presentation. But today I'd like to talk about our applications about global warming, if this is real or fake. And I guess, and I believe, especially here in this room, everyone knows that this is real, okay? And then I just share here with you some news. In Brazil, okay, we have a big forest important to our planet, Amazon, that's suffering a lot with the climate, okay, crisis hitting our country. We have many disasters occurring in Brazil from the south to north, We have many aspects, okay, showing us the importance to take care of our planet and this climate crisis. But also, recently, we could see that these occurred in US, United States of America. In LA was like fired, and this was connected to climate change by scientists, as you can see in this news here. But in India too, okay, we can see news from India. This is from the New York Times, okay, where landslides, okay, in India made worse by climate change. This was like reported by also scientists. So we have many disasters occurring around the world, okay? And the question is, this is not fake, this is real. And this was, for example, awarded in 2021, where the Nobel Prize in Physics, okay, was delivered to this guy here, Sirocco Manabi, Klaus Aussermann, and Giorgio Parisi, for their contributions, okay, to our understanding of complex systems. So climate change and the emissions of gases into the atmosphere is a kind of a complex system, okay? But this guy around over the years have shown, okay, the role of greenhouse gas in climate change. So proving that this is real and the warming is occurring due to the increasing of the temperature of the planet, exactly due to greenhouse gas emissions. So, but the question is how to solve this challenge, how we can deal with that, okay? Because of course we have many problems and drawbacks, okay, to deal with. And I'd like to show and share this important paper published in Nature Reviews in 2017 by Professor Emily Carter, where she says, or better, she said, here in this paper about quantum solutions for a sustainable energy future. And specifically in this paper, that was like important to me to visualize that the development of advanced quantum mechanical methods, which can be combined with other simulation tools, afford insights that will help to secure our energy and environment future. So this perspective published in Nature Reviews in 2017 was a kind of proof to me that my decision 2010, okay, as I told you here in my presentation, that winter school was quite important in my career because I was like right deciding to work with quantum solutions and simulations to tackle many problems in the world. So also recently, exactly in 2024, the same researcher, Professor Emily Carter, published this opinion in Jake about our role in solving global challenge. And she pointed out five, okay, five problems that you need to think and try to new solutions to solve. One is about climate change, including mitigation, adaptation, and intervention. Another one is environmental degradation, including waste and recycling. Energy transition, including efficient electricity generation, transmissions, and storage in carbon neutral fuels. Fresh water and food scarcity, including sustainable water production in agriculture, and infectious disease and human health. So this paper, when I read it, was like, wow, amazing. I'm on the right way, okay, and working on the right way. Because if you, for example, look our website and if you look the publications we are producing over the years, they are exactly about these topics, okay? But this, in these presentations, I'm I'd like to highlight, okay, especially the problems about the climate change and CO2 and some environmental degradations and where we can, how we can um, do to solve this problem. And I, I'd say that we can, of course, we can use many things, okay, to reduce, for example, the CO2 emissions and try to develop new materials and molecules to capture CO2, but more than capture, we can also maybe convert CO2 and fuels. But of course, one important tool to work with that is the molecular simulation, okay, that can work with global warming, as you can see in this perspective. So then, our research group, okay, is working from the quantum to macro scale. So we are working over this scale in terms of the materials, working with the small, quite small systems where we can use quantum mechanics to study these materials. But also we have developed and also we have applied many atomic and mesoscale simulations by molecular simulations using the classical mechanics or the hybrid of classical mechanics and quantum, and going to the macro. In this presentation, I want to talk more about atomistic and quantum. But for example, in my postdoc project, I developed a code where we can simulate the systems by atomistic and also by continuum, okay, equation. So here is the scale and time. So going from quantum to macro, we can run systems more fastly, while here we need to work with small size and quite small time in simulations. So to deal with that, we have in our research group, or at least uh, recently, we have applied EFT calculations for gas, oil phase, also semi-empirical. So basically trying to solve this equation by electronic density, especially when we are working on with the large systems with many electrons. In our research group, we are specifically using Orca and Psi4 for the gas, okay, these two packages for the gas. DFNXD for the semi-empirical, and the quantum espresso for this solid phase. So we have others packets that we can use, but in our research group, we are using this one. From the molecular dynamics and non-equilibrium molecular dynamics, mainly so for solving these equations, this Newton equation. So in our research group, we use ROMAX and OpenM, also LAMP, and other homemade codes written in Bash, Perl, or Python, and Fortran. So for processing the output files or output, okay, the results that we are producing from quantum or classical simulation, we use quantum theory of atoms and molecules approach using this equation here out by this side to exactly to see some quantum descriptors and try to characterize in detail the interactions. I can show you some results. So the applications for CO2 is quite challenging because mainly in our industry today, the main process is based on amine solvent, okay, and physical solvents. So of course, this type of technology uh, has a small cost, okay, in terms of money that you can spend. And of course, also these technologies quite well developed and introduced in industry, so we have a few times to implement and use it. The problem that the problem of that technology is because amine solvent is volatile and then can produce a lot of problems in the environment and also in the equipment industry because it's quite corrosive. Okay, so we need to try to see or to find or at least to discover new technology, trying to go through these pathways here until chemical looping or biofixation approach. Because as you know, for example, the nature, the plants can capture and convert CO2 quite efficiently in cellulose, okay, in plants. They basically use a protein called ribitol that can convert CO2 and hydrocarbonates, okay? But of course, this takes a lot of time, and also uh, the benefit of reduction costs is increasing to this fact. So in our research group, we use it by the first time ionic liquids, also a metal organic framework, try to capture, okay, CO2 from industrial streams, also from the atmosphere. So the first study that we developed was in 2013 by Hunan that basically performed many molecular simulations and trying to study the solubility of CO2 in ionic liquid. And systematically, Gianni Damas investigated by quantum chemistry many ionic liquid classes, compounds, to be applied for gas capture and separation. So I can show you some results, but before that, I'd like to say that Tuano was my PhD student and today is a postdoc at the University of São Paulo. I spent some time in Germany doing postdoc as well, and Gianni Daman today is a researcher in Chopin, Sweden. He is a position there working um, in her research. So Gianni did a very excellent study in her master project, exploring many cations, as you can see by left side here, and other anions, as you can see by right side here in my screen. So we calculated binding energy in kilojoules per mole by quantum mechanics and interactions of cations and anions with CO2, SO2, and H2S. The idea here was try to see the best candidate from ionic liquids to capture selectivity. Okay, for example, CO2 has an SO2 and H2S, okay, in this cell stream. Because I don't know if you know, but here, for example, in Brazil, our oil and natural gas contains a lot of H2S, okay, in the stream together with CO2. So if you want to capture CO2, you need to capture this selectivity against H2S, for example. That work was like quite important because generated many important conclusions. For example, here in red line is the bind energy where we can separate the physical absorption and chemical absorption. So less than this value, we have mainly physical absorption, okay, systems, and higher we can apply this as chemical absorption. After this work, so we could see many other experimental work being developed where the people try to explore some anions, for example, for chemical absorption and so on. And these publications in Chemical Review in 2017 cited work as a support for this picture where they explained the strong ion cohesion in ionic liquids, okay, producing and uh, small cavities, small empties, okay, the ionic liquids. So to like tune and design new ionic liquids capture CO2, we needed to exactly have ionic liquids, okay, with weak ion cohesion, okay, producing more cavities in the systems, and then um, having the possibility to uh, get this CO2, okay, more and more. So exactly about because the binding energy between the ions, okay, that was exactly our main goal here in this study in 2014. They cited these important roles to play with ionic cap capsules. So, but also we have not only this problem to show you. Also, we have like worked with many other materials capture CO2 and also other applications that we are working on. So I can, for example, share with you here this work from my ex-PhD student, Flavia, that developed simulations for polyurethane urea oligomer model, okay, to try to capture CO2 and CO4, natural gas, okay, um, industrial stream. They developed a nice and very good protocol to do that. Also, we worked with the energy and storage energy and batteries, lithium metal batteries. UNM developed these important interfacial structures in ionic liquid phase generally electrolyte for lithium metal batteries using molecular dynamic simulation. We have many others, but of course, in this time, it's impossible to show you all things that I want. Okay, so if you click on here in QR code, you can access the paper. So also, it developed nice and important work together with experimental scientists, where they basically used many co-solvents with water to try to improve the exfoliations of graphene. So in this study, we could show exactly the mixture. Exactly, we could see the perfect mixture of the secret pure done and water mixture to better exfoliate the graphene. Okay? Because I don't know if you know, but if you exfoliate graphene in pure water, basically the layers will attach one each other. So you need to exfoliate and separate the layers perfectly to produce your material. So for that, we need to use co-solvent. And one co-solvent used was exactly this one here. And then from the simulations, we could explain the mechanisms to exfoliate well the graphene. So also with CO2 and these produced the pattern because in this study we combined amine and also glycerol to like waste to not exactly glycerol is waste, but amine is quite cheap, okay, raw material from the industry. So using the glycerol, that's a problem to deal with, and then we could produce, okay, a new product reacting with CO2. In this exactly this is the conversions of CO2, okay, in a product. And this product was an ionic liquid, as you can see here, again, carbonate and this amine. So that was amazing and quite important research that was led by Professor Celia Ronconi, and I have as a collaborator Professor José Valdemar. Also, you can click on this QR code here and see the paper. So I'd like to share this nice work here with you because Panir is here in the room, and Panir came to our research group in 2001, exactly in the pandemic period, and over the year over the years we developed a very nice and important friendship. Panir is a very friend I have today, and he has developed very good works and many research here in our group. And together with Professor Fred from Papa J, when he investigated CO2 electron reduction mechanism using a kind of method, manganese diamine catalysis is not a novel method, so it's important to attack this problem by not like quite expensive metal like uh, gold or platinum or palladium as well. And then in this work, Panir studied, investigated this catalyst, okay, to convert CO2 in many other raw materials, like, for example, synthetic gas, monoxide, carbon monoxide, methanol, for example, for the acid and so on. So Panir explored exactly the reaction mechanisms for each pathway here by quantum chemistry calculation. So this is exactly the type of results that we can, for example, uh, find from computational theory. And then in my title, as you could see, we have designing materials, but what about designing new materials? Okay, in my talk. So for that, I'd like to say to you, and I guess everyone here in this room knows that we are living now a kind of a digital revolution. So around the world, as you could see recently with the generative AI, okay, and the fight between many big companies like Google, ChatGPT, and DeepSeek, and so on. Of course, we have many others examples to share. But exactly, we are exactly in the present and nowadays, we are living kind of a digital revolution or a war digital revolution, okay? And then for that, the matter simulation uh, will be or exactly is today a revolution, okay? And not more evolution because evolution occurred in the past, but we are living and present in the feeling a kind of a revolution to design new materials exactly using computational chemistry techniques. Exactly because quantum chemistry is a consolidated area, consolidated research, okay, where is interconnected with physics, chemistry, applied mathematics, and computer science. In this paper, Alan Aspudoguchi, okay, it's a kind of a visionary guy and research that said for us that we will experiment. Okay, this is in 2018. Now 2025, we are 2025. We are exactly looking at this revolution experience in our day. So we are exactly living a kind of a new era that we can call chemistry 4.0. And then with that, okay, 3, 4 years ago, we started to work with artificial intelligence and machine learning that became a kind of new research in our group, okay? And the new tool that we developed was PDF mechanical. I believe soon, Okay, you can have access by GitHub. Now it's close to us because we are finished the patent to it. This is a kind of machine learning algorithm that can use natural language processing to extract from the PDF, okay, files, for example, structure, okay, molecule. For example, exactly in our project, we are using as an example a kind of organic synthesis lab, where the researchers over the years have produced a lot of molecules, synthesized a lot of molecules that are published in the PDF files and many others. So with the PDF attempt, we can read, okay, millions of PDF, thousands, millions of PDF, okay, and extract the 3D structure of molecule, okay, and build up that database with this algorithm, where this database can be used by machine learning algorithms to predict properties. So with these applications, we can predict the properties of some molecules, for example, for a target, a disease, for example. Also, we are developing, using this same protocol, other applications in mining and so on. So we have a kind of database, this website here, where people also can insert, okay, zip file containing PDF files, name, and then the PDF chemicals can generate a chemical from the PDF and build a database for you. So here we have, for example, some structure of the constructor. So this is application of our research group using the machine learning, artificial intelligence, okay, development. But I'd like to highlight this, showing you the Royal Society of Chemistry report, where they published quite recently, okay, in 2000, last year, they published a kind of a guide about the digital future and the chance that we will pass about the discovery, sustainability, talent, and knowledge. But specifically in this report, I'd like to highlight these 5 topics here where the Royal Society of Chemistry, okay, like is saying to us that we need to pay attention, please. Computational modeling and simulation, imaging and visualization, machine learning, artificial intelligence, advanced measurement, sensing, robots, and automated systems. And then we can say like automated lab, chemistry lab. This is not the future. This is the present. So we need to be prepared for the future, and we need to pay attention on these skills to build a sustainable future, and of course, use by the best way these tools. And with that, some universities in the world, I guess, started was like the first, okay, to start with that. And I can share with you that Imperial College London exactly was or is the first university, okay, in the world where they are forming postgraduate, okay, students in a master program about digital chemistry with AI and automation. After Imperial College London, other universities started this. But the interesting is they have in on the website these highlights, okay? Discover how advances in automation, artificial intelligence, and big data are revolutionizing the study of chemistry. Learn how to implement machine learning strategies to solve problems in chemistry, drug discovery, and material science, and benefit from a flexible blended learning program before applying your skills in extensive research projects. So with that, here in our, for example, institution, I started a course in for the undergrad student, also for the post-graduation student teaching, for example, coding, programming Python for our students recently. Exactly in this period, I will give this lecture again to the students. But it's interesting because, for example, University of Southampton created a bachelor in chemistry focused on digital methods and computational modeling. So these people here, everyone, this is the future. So we need to think about that developing new materials or new drugs, okay, we can reduce time and focus using by the best way digital methods or computational modeling. So with that, it's this visionary man, Richard Feynman. I have a great inspiration on his life and his career. Published a book, okay, a business book with the title "Simulating Physics with Computers." And Sir Richard Feynman said, I want to talk about the possibility that there is to be an exact simulation one day, maybe, that the computer will do exactly the same as nature. So maybe, I don't know, Richard Feynman, okay, was right. And I guess the development that we can see in the near future could help us simulate, okay, the systems in nature quite close to the exact way to live. So with these presentations, I'd like to talk about some conclusions, okay? So building a peaceful and sustainable future requires a range of competencies that go beyond, for example, being ready for jobs, but people need to have a great deal with social and environmental awareness, okay, as well, ability to cooperate, negotiate, and find creative solutions to new and old problems. Growing reliance on artificial intelligence, skills such as complex problem solving, critical thinking, with creativity, people management, and emotional intelligence are increasingly viewed as some of those most reliant or infused human values. If you have this together with the technology we have on our hands, with the molecular modeling artificial intelligence, of course you can. Probably you can design, you can be able to design new materials or new drugs for our sustainable future. So I'd like to thank our research group and the guys that can, of course, they exactly are responsible for these results, okay, and highlights that I shared with you here. So we have two pictures of our like meeting, have many postdocs, PhD, master, and undergrad students in our research group. Of course, I like to thank our collaborators, okay, here in Brazil and also over the world, okay, in many other universities. Thank you to everyone for this and also for our the people that and the funding agencies and companies that can help us with the budget to work with the research project. And please, thank you, obrigado, Nandri, not Nadri, Nandri, and how to call. Okay, thank you.